All right, for today's lesson, we're going to figure out how to find the area of a parallelogram if we know three pieces of information. First, if we know that what the lengths of two of the sides of the parallelogram is, and then if we know what the measure of the angle theta is between those two sides. So let's first talk about traditionally how we figured out the area of a parallelogram. If you remember back from your time in geometry, we were given the formula that the area of a parallelogram is equal to the base times the height. Real simple formula. Okay? Now, in the case where we have the measures of two sides and the angle in between, we don't have the height here. Really, we only have the base. So we're going to take a couple of different ways to figure out what is a new formula, and then we're going to show that those two ways get us the same formula. So the first thing I want to do is I want to take this parallelogram and I'm going to add, remember what we called an auxiliary line. In this case, the auxiliary line that is the diagonal of the parallelogram. So here, let's take that and I'm going to do it in green here. I'm going to add the diagonal in. Okay. Now, what does this do for us? Well, as you can see, it separates the parallelogram into two triangles. I'm going to show you that these two triangles are actually congruent to each other. And this may be something that you remember from geometry, but I'm going to take the time to show you again, just so we're remembering how we do these types of proofs. Always good to go back to geometry and figure it out. And I'm going to say that this diagonal, I'm just going to call that side C. And now let's remember back to our definition of a parallelogram. Parallelogram is any quadrilateral that has opposite sides that are parallel. And as a consequence of this, one of the theorems that we learned back in geometry was that not only were the sides parallel, but they were also congruent. So that means that this opposite to the B here also has a length of B, and the side here that's opposite of A will also have length of A. Now in this case, then we have two triangles that have three sides congruent, remembering that by the reflexive property of congruence, that side C is congruent to each other. So we have A congruent to A, B congruent to B, and C is congruent to C. And thus by side, side, side congruence, we know that these two triangles are congruent to each other. So this triangle here, the red triangle, this triangle here, the green triangle, they are congruent to each other. And one of the things that we know about congruent triangles is that they have equal area. That means that we know that the area of the parallelogram is going to be equal to 2 times 2 times the area of these smaller triangles. And now for this red triangle, we know 2 of the sides and the measure of the angle in between. So by the formula that we learned, we know that this is going to be 2 times 1/2 length of A, length of B, sine of theta. And thus, if we just cancel out that 2 and that 1/2, the area of a parallelogram works out to be A times B times sine of theta. So it's always just going to be the product of the lengths of the two different sides times the sine of the angle between those two sides. Now, if we thought about this using this old formula here, using our area equals base times height, well, here we are in a situation again where our height, we can, right, draw a height line here, recognize, right, that since it's an altitude, it forms a right angle to that side B. And then here we're going to know, as we've been doing all along, that then the height of this triangle, much like the height of this parallelogram, is going to be a sine of theta. Right? It's going to be the hypotenuse that forms of this right triangle, the hypotenuse times the sine of theta, and thus we get the same result going by our old parallelogram area formula, that if we substitute in this h for h, we'll get a times b times sine theta. Right? So it's an easy formula since we already know the triangle formula. All we're doing is we're taking away the 1/2. So parallelogram is going to be the measures or the lengths of the two sides times the sine of the angle in between them. Now, one of the consequences of this area formula for parallelograms is that we can actually use it to show that two supplement angles must have the same sine value. So again, I have up there our formula that the area of parallelogram is going to be equal to the product of the two different length sides of a parallelogram times the sine of the angle in between them. Let's go look back at the parallelogram that we had. And we're going to recall from geometry that two consecutive angles of a parallelogram are themselves supplement to each other. That means that this angle here, theta, and the angle in green here have to add up to 180. So that means that we could also write this angle here as 180 minus theta. Okay. And now remember that since the length of this side is b, since it's a parallelogram, the length of this side is going to be b. So now we can come up with two different ways to describe the area of this parallelogram. First is going to be this one that we used up here. Right? We use side A, side B, and our angle theta here. But then another formula for the area of this parallelogram is going to be, again, A times B, because those are two adjacent sides, but the angle between them this time that we're going to consider is this supplementary angle. So we can do it now as sine of 180 minus theta. And now for a parallelogram, the area of that parallelogram is constant, right? Nothing changes about that area if we just find it a different way. So I can take these two formulas, and by the transitive property, I'm going to set them equal to each other. So I now know that AB sine of theta is going to be equal to A times B sine of 180 minus theta. And if I just divide through by that AB that's on both sides and cancel them out, we get the formula at the end that sine of theta is going to be equal to sine of 180 minus theta. And here is proof right there that the sines of supplementary angles are equal to each other.